Okay, so we stopped here yesterday when we were discussing the diameter, but I think I might just go back a little bit just to sort of give a refresher, especially with regards to this one. So hopefully you all recall this. This is given a network, you can represent the entirety of its structure in terms of an adjacency matrix, right? So what the adjacency matrix basically tells you is what are the connections between every node to any other node. There's a 1 means there's a connection, 0 means there's none, right? And the utility of the adjacency matrix will become apparent. I mean, the more you explore the topic, but the most basic information that you can get from it is the degree, right? So essentially, by summing along the rows or the columns, you can get the total number of connections that a node has, right? You see here that you take the sum of aij over all the i's, all the rows, or all the columns, you get the degree, right? Of course, for an undirected network, this is the same, because the sum along the rows, the sum along the columns will be the same. But for a directed network, whether you sum along the rows or the columns, it will give you either the in or the out degree, right? But the number of connections that are so actually the out of the in degree. So the number of connections going out of the node, the number of connections coming into the node. Right? So yeah, so that's the adjacency matrix. Then I had discussed here so about the shortest path then, right? Just to recap, a path is basically like a route that you can go from one node of the network to another node in the network, which does not go over the same edge twice, right? So if suppose I'm going from, let's say, 1 to 3, a path could be like 1 to 2, 2 to 4, 4 to 3, right? So I can't go from 1 to 2, 2 to 4, 2 to 5, 5 to 3, 3 to 5, and so on. So it's just the hops that you can take going from one node to another without crossing the same path, same edge twice. And the shortest path length is the shortest path that exists between two nodes, because you can have many paths. So you can have from 1 to 3, you can go like there's a bunch of different ways that you can go from 1 to 3, but the shortest path is the shortest way that you can do that. And of course, one can compute this for every pair of nodes in the network, and the diameter is basically the longest shortest path, right? So basically it'll tell you something about the spatial extent of the network, like what's the least number of steps that you need to take to get between the two furthest nodes of the network. That's one way to think about it. Okay, so this is roughly where we had stopped yesterday. There's another quantity which sort of follows on from what we were just talking about, which is the average path length. And this is actually very simple. If you know the shortest path length, the average path length is essentially just the average, right? So if you have, if dij is the shortest number of steps between node I and node j, then the average path length is basically just this, right? So basically this normalizing factor times d. So hopefully people understand where this normalizing factor comes from, right? Why do you have an n times n minus 1? Yeah, yes, that's right. So basically you can have this is you can think of it like suppose you have a fully connected network, right? So basically all nodes connected to all other nodes, right? And if you have n nodes in that network, you'll have how many links? Like how many links will there be in that network? Sorry? Yeah. Then yes. So basically that's just that, right? So at most you can have that. So basically, so suppose in that network you take the sum over this, you would get n times n minus 1, and so then that would be 1, right? So that's why you have this as a normalizing factor. So right, okay, so then that's very straightforward, right? So basically you look at all the possible, all the shortest paths between every pair of nodes in the network, and you normalize it, and that's your average path then. Okay, so if you understood that, then you should be able to tell me what are the average path lengths of these networks. Can you who wants to tell me about the first network? What's the average path length for this network? So remember, you just have to sum over all the shortest paths, right? And normalize it by n by n minus one. So n is the total number of nodes. So in this case, for example, here it's 3, right? So you can at least do that, right? So you can find the normalizing factor and then tell me what the L is going to be for this network. Sorry? So okay, what's the normalizing factor?
6.
1 by 6. Okay, good. And then this?
4.
I see number of answers. What is
8.
8? No, so remember there are 3 nodes, so basically there can be 3 paths. Basically, so we have, let's say, this node, this node, and this node. So one path from here to here, path from here to here, and a path from here to here, right? So these are the 3 possible paths.
But from the reverse, from A to I, so it's not like from 1 to 2 and 2 to 1, you double count.
So
Yeah, then the coordinate to the next
well, but you also have links going. Okay, let's see. So suppose you have so there's 1, 1, and then a 3, 4, and 4 by and then there'll be 6, right? So that's 2/3.
Average path length is the characteristic of the graph.
It's a parameter graph, yeah.
So when you sum over dij,
Yeah.
so if you put 2, then you have to divide by 2 in dij, right? But you like so this will get the same answer, but you are just double counting.
Yeah.
But you're double counting in the denominator as well, right?
Yeah, so you're double counting.
Yeah, you're double counting in both cases. Yeah. So that's how it is. Okay, so anyone wants to try this one? Yeah.
Take 2 plus 2 and 0 and 1. We will say 1 is the first current. Take 1 to 3 and 0.
You did say
No, I think it will be ij. Okay. I think yes. Sorry, I think there should be a factor of 2 here because then you will that way you don't because you have yes, because then otherwise it will be 1, right? So yes, sorry, you're right. Yeah. So you have to there should be a factor of 2 over here as well.
Definition will also work for directed networks.
This direction will work for directed networks. Yeah. Sorry, that's then so basically the this is counting all the paths that exist. Yes. So I think the issue is basically with this over here. So when I say I not equal to j, but it's all the uniques I and j. Okay. So basically, so the answer for this would be basically one connection between node 1 and 2, one connection between node 2 and 3, and then one connection between 1 and 3. So there's length 1, and then length 2. So there's total is 4, and so then divided by 6. So that's what it'll be for this this network. Yeah.
but here we are counting on the 3 pairs.
For an undirected network, basically, so you just consider the link as a whole. So basically, you just have between these two nodes, there's one link. You consider that. These two nodes, another link. You see, look at that length, and then between this node and this node, there is just one path, and you just consider some of that path. Yeah.
Then we are only counting 3 pairs. So it would be 4 by 3.
No, it's 6 over here, right?
But that's 6.
Everything.
6 is assuming we are double
We are doing directed graphs if we're writing 6 there.
Yeah.
What if we just say in the normal case we just say okay, this is this path is this length, this path is this length, this path is this length, and divide by number of paths would be and choose to take number of edges.
Yeah.
And
So that would be 4.
then there would be a 2 factor there, so that 6 problem won't be there. That 6 will become 3, the number of the summation of that distances comes out to be 4, so it will be 4 by 3. So we just have that 2 dividing the.
It should be clear what I said. I'm not saying that you should divide this by 2. I'm saying the problem is actually here in this I not equal to j. What actually this is saying is the total number of links that you need to go between every pair I and j. That's what it's saying. So the factor of 2, it's implicitly there's a factor of 2. It depends on how you say it, but what I mean is that between every pair of nodes, you consider every possible pairs of nodes I and j. So here there are 3 nodes, 3 pairs, and then you just take the path length of along that pair, 1 and 2. That's what it means. Yeah.
If you take a pair,
Yeah.
then you don't have j.
Yeah, it's just a pair, exactly. Yeah. So I think so the issue is so it's just that you consider one pair at a time, ij. So you consider each unique pair basically. Unique pair each
There's no restriction.
I, j and j is the same pair.
Unordered string also will contradict create some problems in definition and static state agents.
Yes, of course. Yeah. Okay, so sorry about that little bit of confusion, but basically, so I think the issue is coming in this term over here. It's essentially every pair I and j. So you look at that pair and you take the length of the shortest path length along that pair, take the sum across all of that, and then scale it by this, which is basically the maximal possible number of things. So so that's that. Yes. Yeah.
It's being counted, but J and I is not being counted.
It's the same. I mean, we're assuming it's the same pair. I mean, we're assuming it's the same, right? So I
I to J, I'm not counting that J.
because this is an unwritten network in this case.
Right, but then this
You
should
should count.
There should be a factor of 2 if you're doing that.
because the average path length for the first graph
Yeah.
will be 2 by 3, which is less than 1.
Yes.
That doesn't make sense. It has to be 4 by 3. Should be greater than.
Like if you're counting just the unique pairs,
Yeah.
if you're counting just the unique pairs,
Yes.
the normalization factor should be 2 divided by n. Yeah. So n choose 2 is n minus 1 by 2.
So the 2 goes. We are counting twice.
I'm saying if you're not counting this, then n choose 2 and n minus 1 by 2.
Or we can just say that I is getting j. I.
Both are equal.
Both
Yes.
are.
Sorry about the confusion there. Okay, so that's the path line. Okay, so let's so one can use the same procedure to work out for the other types of networks as well. Okay, so now let's move on to something else. So so remember, we can also look at the like different walks or different lengths between nodes, right? So basically, if between every pair of nodes in this network, one can have a walk, right? So basically, you can go from 1 to 2 to 4 and so on. So if you look at all the walks of length 1, right? So what are the walks that are possible? So basically, you'll find that essentially this is just the same as the adjacency matrix, right? So basically, if you have a walk of length 1, it means you go from let's say node 1 to 2, 2 to 4, and so on, and you just list all of that, and you find that this is just essentially just the adjacency matrix. So it's kind of obvious, right? It's almost like the definition of what the adjacency matrix is. Right? If you look at walks of length 2, then you will see that so let's say from here 2 to 3, right? So you can go from 2 to 4, 4 to 3. That's the walk of length 2, right? Another is 2 to 5, 5 to 3. Another walk of length 2. So now you can write down basically all the possible walks of length 2 between every pair of nodes in the network. And actually, you notice like here along the diagonal, you see that it's no longer 0, right? So for example, from 1 to 1, there's a walk of length 2. You see how that is, right? Basically, go from 1 to 2 and back to 1 again, right? From 2, you see it's 3. Basically, 2 to 4 back again, 2 to 1 back again, 3 back again, 5 and back again. In fact, essentially this along the diagonal is just the degree, right? Just the total number of links that this node has. That's what's along the diagonal. So so one can construct one can obtain all the possible walks of length of any given length between all pairs of nodes in the network. but for a network which is very small like this, one can easily do this. But then in general, well, even if it's small, it starts to become a bit of a bit tricky once you have a large number of walks, right? So the question is, how does one like find the total number of walks of some length d between every pair of nodes in the network? Is there some sort of simple way of doing this? Yes, that's on the next slide. Yes, that's how you do this. So basically okay, so basically let's break this down. So suppose you want to go from node 2 to 3, right? So from node 2 to 3, and we need to have a walk of length 2, right? So how do you get there? Basically, first of all, you have to say all the walks of length 1 from node 2, right? So basically you say that I go here, I can go here, I can go here, 3 places, right? So that's what's listed over here. Of course, this matrix, remember, this adjacency matrix is for an undirected network, so I could either had marked this row or this column, it doesn't matter, right? But for now, let's just say I'm looking along this row, and you see I have a link from 2 to 1, 2 to 4, and 2 to 5. Okay, so now I also need to reach 3, right? So how do I reach 3? Well, I can reach 3 from 4 or from 5, right? So if I just look at the same adjacency matrix, but let's say look along the column, and along 3 I say no, I can't get there from 0, not from 2, so from 1, not from 2, not from 3, but I can get there from 4 and 5 in one step. Okay, so basically I have to go from 2 to one of these other nodes and come from one of some other nodes to 3. So how do I get there? Well, basically if I just take the product, right? So so going from, let's say, 2 to 1, and then 1 doesn't get to 3, so the product of that is 0, right? Then 2 to 2, well, it doesn't go anywhere. 2 to 3 doesn't go anywhere. 2 to 4, okay, there's a link. 2 and 4 to 3, there's a link. Okay, so that's one person. Then 2 to 5, yes, and 5 to 3, yes. So if I just take the sum, right, of all the products of of a of 2k and a of k3, right? So basically second row kth column, kth row third column, right? And I take the sum of that. That gives me the total number of paths of length 2 between nodes 2 and 3, right? And I'm sure you can all recognize that essentially this is just a matrix multiplication. So basically doing a matrix multiplication, so this is for this particular entry, but I can do this for every possible entry, and taking the matrix multiplication is going to give me for a matrix that will tell me the total number of paths of walks of length 2 between every pair of nodes in the network. And then I can just extend this in general, right? So basically a times a times a times a d times that will give me some matrix, and that is going to give me the total number of walks of length d between every pair of nodes in the network, right? So this is actually a very simple way of finding the total number of walks of a given length. Now you so things like looking at the shortest path length and so on now become a lot easier, because now you can just use matrix multiplication and you can find things like that. Of course, there's still you have to be a little bit careful while you're dealing with this, but it's a lot easier than just counting, right? Because that's something which you can do for only very small networks.
The directed part.
Yeah.
So both multiplying left and right.
You have to be careful in terms of which is why I did it like this. I did it along the row over here and along the column here, because the rows I mean, if you have a directed network and I'm having the sources along the rows, then this will be the source, right? So coming out of 2, and then the columns will be the target, so coming from somewhere into 3. So yeah, so it would still work in that case as well, right? Okay, good. So this is like a procedure that you can use for this purpose. Now another thing that you can do to find the average, the shortest path length, or just the path length, sorry, the path length is what's called the breadth first search method. Now for small networks, this is actually a fairly computationally efficient thing, but of course as the network size becomes big, this is maybe not the best, but you can, it still does a fairly good job. So essentially to find the shortest path between a pair of nodes I and j, what you do is that, so you start from some, let's say I'm starting from node number 7, right? Then what I do is I say, okay, so which are the nodes of distance 1 from node 7, right? So basically here I find that it's 5, 6, and 8. And this I can find from the adjacency matrix. So this is quite simple. So I find that, right? And then I say, okay, so then I'm going to like discard this 7. I'm going to say, so that's the source. I don't need to worry about that. And then now I'm going to just label these 3 as green. So say, so this is now the new set of nodes that I need to look at. So I'm going to look at these 3 nodes, and then now cycle through each of these nodes, so 5, 6, and 8, and find all the nodes of distance 1 from them. So I find that 8 has no neighbors, but 5 has 1 neighbor here, and 6 has 2 neighbors, right? So then I label those neighbors. So it turns out that so so now by just 2 steps I figure out all the nodes of distance 2 from node 7, right? So you can check it yourself. So these are all the 3 nodes that are distance 2 from node 7. And then one can keep doing this. So then say, okay, fine, let's discard 5, 6, and 8 because that's done. So I know that 5, 6, and 8 are distance 1. I know 1, 4, and 3 are distance 2. And then follow this procedure again. I say, okay, so 2 is of distance 3. So I just, and one can keep doing this and find all the distances between every node starting from a given node. So this is another thing that one can do. But of course, one has to do this separately for each node that you start with. But this is quite a fast thing, because here you're not even doing matrix multiplication. You're just looking at the adjacency matrix. Right? So this is another thing that one can try to do. Okay, so let's talk about another attribute of the network structure, which is what's called the clustering coefficient. So this is something which we noticed yesterday, which is that people from the same institute tend to talk to each other. This is, we don't worry about this. This is normal, but it happens, right? So and in any social network, this seems to be very common. Like you tend to be friends with, you tend to sort of interact with people who you already tend to know, and of course this is something that's true much more widely as well. Right? I mean, across different types of real world phenomena, which which have some sort of network structure, you find that nodes form links with nodes which the neighbors are also links to, right? So suppose I have a friend and he has another friend, then it's possible that I also might know him and might be a friend of this person, and but to what extent is this actually happening in a given network? One can actually measure this in terms of what's called the clustering coefficient. And so the clustering coefficient, essentially one can look at from 2 different ways. One can look at it from the perspective of the whole network, which is what's called the global clustering coefficient, or one can look at it from the perspective of each individual node, and that's called the local clustering coefficient, which I'll also come to in a second. But for the moment, just focusing on the global clustering coefficient. Essentially what this is if you look at all the fraction of paths of length 2 that are closed, that's how you can calculate it. So basically, let's look at this example over here. So this is a path of length 2, right? So basically going from 2 to 5 and 5 to 4. And I say that it's closed if there is also a link going from 4 to 2 as well. Okay. So here's this is closed. But in this case, so going from 2 to 5 and 5 to 3, there's no link between 2 and 3, right? So it says it's not closed. So in this way, I basically look through all the paths of length 2 and check if they're closed. Okay? And so a triangle of nodes will basically contain 3 closed paths. So basically, so let's just look at this 2, 4, and 5. So basically, I have like one path like this, another path like this, and another path like that, right? So I have three closed paths. So you can actually reframe the definition given above like this. So just look the 3 times the total number of triangles which are there in the network. So a triangle is basically just three nodes all connected to each other, divided by the total number of connected triples, right? So a connected triple is basically the path of length 2 which is either closed or not closed. So for example, 2 to 4, so 2 to 5 and 5 to 4, is a connected triple, and 2 to 5 and 5 to 3 is also connected triple. It just means that you have 3 nodes that form like one path. It's just, or in other words, it's just a path of length 2. So that gives you the clustering coefficient, right? And yeah, so basically, but this is a property that is at the level of the whole network. But one can also look at this from the perspective of the individual nodes of a network, right? So for that, what you do is you look at a given node and look at its neighborhood. So here 2 is a neighbor of 4, 3, and 5, and then you see how close the neighbors of 4, 3, and 5 come to a clique or a completely connected subgraph. So over here you see that this is a clique. Basically, 2 is neighbor has. I'm sorry. Wait. Sorry. No. I misspoke a bit earlier. 2. Sorry. This is a clique. So basically, 4, 5, and 3. That's a clique. But these are not neighbors of 2. Yeah, so I was just showing an example of what a clique is. But here, if you look at this, so this node has these 3 neighbors, and we're now going to we need to see how many of these neighbors are connected. Is it 0, 1, 2, or 3, right? So if all 3 of them are connected, then the clustering coefficient is maximum, and so on, right? And so we see that there can be a maximum of k times k minus 1 by 2 links between them. So suppose there are k links. So these are the maximum number of links between them. And yeah, and so basically we just look at the fraction that exists. So let's look at some examples. So let's look at this case, for example. Right? So basically this node, blue node, has 2 neighbors, and what's the clustering coefficient? 0, right? So basically there's no connection between them. What about here? 2 by 2 by, yeah. So basically there are three neighbors. There's a one connection between them, but this connection is absent, so it's 2 by 3. What about here? What with, right? Because there's only these two have a link. Yeah, there's no link from here to here to here, or yeah. So basically those 2 links are missing. Right? So that's very simple. Okay, so here are some slightly more challenging ones. So what about this case? So basically here we have a ring, and the each node is connected to its 2 neighbors on the left and to the right, but also to the next nearest neighbors, the one over here and the one over here. Okay. So in this case, you can see that essentially every node has got the same sort of neighborhood structure, right? So basically, if you look at any given node, it will have exactly the same kind of neighborhood structure as everybody else, right? So in other words, it should have the same clustering coefficient as everybody else. They should all have the same clustering coefficient. So for a given node, let's just say for a given node in this network, can you find the clustering coefficient? So remember, so let's say this node over here has 1 neighbor and 1 neighbor, 1 neighbor, 1 neighbor, right? So it has 4 neighbors, right? And you just have to look at the links that exist between these neighbors, which is how much? 3, right? So basically you have 1 link here, another link over here, right? And what's the total possible number of links that can exist? So basically you have 4 times, right? 4 3s are 12, by 2 is 6, right? So basically this, right? So 4 times 3 by 2, right? 6. So basically it's what? No, this is 3, because you have 1 link here, 1 link here, 1 link here. So 0, yeah. This one, anyone wants to try? So basically, this is just a lattice where all the nodes have 8 neighbors. Basically, you have the north, south, east, west, and as well as the two diagonal ones. What about here? It looks very messy, but if you think about it carefully, actually the neighborhood structure is not too difficult. So first of all, identify. I mean, so you know that there are 8 neighbors, right? So what is the total? What is the possible number of links that can exist between the neighbors? How much?
28.
Yeah, exactly. 28 possible links that can exist, and how many links actually do exist? Sorry, 12. Yeah. So basically, you have 3, 3, 3, and 6, and then no other link between. So 12 by 2. And lastly, how about this one? So this is just basically like a lattice, but you also have one of the diagonal links. So now the degree is only 6, right? So you only have north, south, south, east, west, plus along this diagonal. So there's another 2 of there. So what is the total? So what's the total possible number of links that can exist between the neighbors? 15, right? Yeah, because so 6 times 5 by 2, that's 15. And then what is the actual number of links that do exist?
6.
1, 2, 3, 4, 5, 6, 7. No, it's not. Wait, one second. Yeah, 1, 2, 3. Yes, right, yeah, it's 6. Yeah, it's hexagon. Yes, it's 6. Yeah. So it's 6 by 50. Yeah. So,
8.
huh?
8. In this.
So basically you have like 1, 2, 3, 4, 5. It's only the ring around it, because the middle node is I mean, you don't consider, right? So basically you just look at all the neighbors, and the links between the neighbors form a hexagon. So yeah, 6 by 15. So okay, good. So that's that. So now let's go on to another sort of facet of network structure. So sometimes networks can actually look like this, right? So essentially these are all nodes of the same network, but it turns out that there's no possible way to get from these nodes to these nodes, right? So I can have a path between all these nodes over here, path between all these nodes over here, but there's no path that exists between these nodes and these nodes, right? So the adjacency matrix would look something like this, right? So you see that here so these are all the paths that exist for nodes 1 to 4, and all the nodes paths between nodes 5 and 8, right? In this case, we say that like a pair of nodes are connected if there exists a path between them, right? So these 4 nodes, we say that they're connected. These are connected, but 4 and 6 are not connected, right? And so a component is basically a subset of a network in which all the nodes are connected. So we say that this is one component, and this is another component of the network. So within a component, the nodes are all connected. You can get from any node within a component to another node within a component within a finite number of steps, but not between components. So a bridge is basically if you have a network structure like this, right? So and the yellow link is just highlighted. So a bridge is basically a link which, when cut, is going to cause the network to be disconnected, right? So a bridge is I mean, it has no sort of attributes of its own, except for the fact that essentially it functions as functions as a path which allow some parts of the network to become connected to some other parts of the network. Okay. So so basically these are what are called components. But so in a directed network, sorry, in an undirected network, it's very simple to think about components. But in a directed network, it becomes a little bit tricky, because now you also have directions for your paths, right? So here you see that it's a similar structure to before, but now you have these arrows, right? So you see that clearly it's not possible to go from still from these 1 to 4 to you cannot go from there to 5 to 8. That's still true, but also now you see that you can go between 2, 3, and 4 but 1 you can only reach there. You cannot go from 1 to any of these other nodes. And the same is true over here as well, right? So I can go between 6, 7, and 8, but but 5 I can only reach that. I can't go to any of the other nodes. So in a directed network, I mean, you still have the concept of components, right? But you now have two types of components. One is what's called a weakly connected component, which is that so suppose you just ignore the directions for a second. So just ignore the arrows, and then you just look at whether or not that paths exist. That would tell you what the weakly connected components of the network are. So basically here 5, 6, 7, 8 form a weakly connected component, but the 6 and 7 and 8 are the only ones that form a strongly connected component, and similarly 2, 3, and 4 as well. So a strongly connected component, there exists a path between all these constituent nodes. Yeah. So that's the main difference. But apart from that, it's the same idea as for the case of an undirected network. And you also have two other sort of notions, which is but this is from the perspective of a node, right? So this weakly and strongly connected components are from the perspective of the whole network, right? So basically, say I can divide up the network into different components, but you also have the notion of what's called an in component and an out component, right? Because in the case of a directed networks, you have links coming in and links that are going out. So let's just take a node 2 for example. So node 2, you can reach node 2, in this case only from one node, from node number 1. So this is what's called the in component of this node number 2. But from 2 you can actually reach all the remaining nodes, and so that's what's called the out component of node number 2, right? So it's basically just the sets that you can that either can lead you to a node, or from which you can reach by a node. So that's the difference. Okay, good. So at least up to now, I think I guess this part is quite clear, right? So I think you understood what is components. So if there are no questions, then I have a question for you. So what I've shown over here is a fairly large network. The adjacency matrix, right? So I've shown it in a slightly different form over here compared to what I was showing to you earlier. So now, rather than write down numbers, I've just, because the network is too large to just show numbers, I have represented the network in terms of colors, right? So the white squares represent the existence of a link between a pair of nodes. So you can say that along here, I haven't numbered them, but you can just imagine there is node 1, 2, 3, 4, 5, 6, this direction, and along this direction as well, right? And so the colors, the white represents a connection between a pair of nodes, so between, say, this node and between that node, and black means there's an absence of a link. Okay, so this is just an adjacency matrix. But if I show you something like this, and so this is a fairly large network, but I can tell you, because you don't know this, but I can tell you that this node has a number of components, right? So a component, remember, is a subset of a network where within the subset you can go from one path to one node to any other node, but you cannot jump between components, right? So this node has a number of components. So looking at this, can anyone have a guess as to how many components there are? What, a rough guess? Okay, how many of you say just one component? No, because I told you there's more than one component. Okay, how many of you say there's two components? Oh, no one saying the two components. Okay, how many say there's 3 components?
2 component is there.
Sorry?
You said how many?
No, I mean, how many components are there? Is there 1, 2, 3, 4, 3? Okay. There's 1, 4. Seriously? How many components are there? Okay, actually, most of you are very smart. Okay, because actually it's really stupid to do this. because the point which I was trying to make is that by looking at the network, you can't actually figure out the number of components, except for Harish, who somehow managed to figure out that it's 3. You're right. But the point is, yes, by looking at this, it's really, it doesn't make sense, right? So there has to be a way for a large network to figure out what the number of components are, right? So how do you do this? So the way that you do this is the following, okay? We introduce a quantity which is called the graph Laplacian. So given an adjacency matrix like this, right, so for this network, one can write down the graph Laplacian, which is defined as follows, okay? So essentially, the graph Laplacian has the degree of the node. By the way, this is only true for the case of undirected networks. So this doesn't make sense for the case of directed networks. So you write down the degree along the diagonal, right? So basically that's what's denoted by this one. So basically when I equals to j, you just have ki. So that's what you have over here. And then you subtract the adjacency matrix, right? So basically you have -1s wherever you have a link. So it's essentially, you can think of it as the degree matrix. So suppose I define Dij to be the degree matrix, but the degree matrix is nothing but zeros everywhere, but only ones along the diagonal. Basically, it's just telling you what is the degree of a given node, right? So that's the degree matrix, D minus a. So that's my L, okay? And just incidentally, you can also do this for the case of weighted networks. You could use this definition, but maybe that's not so important for now. The point is, one writes down the one can write down the graph Laplacian for any given adjacency matrix, right? So it's very trivial to do this. So now what do you do? Okay, so what we do is we find the eigenvalues of a matrix. So how many of you are familiar with finding eigenvalues? Okay, good, everyone, great. So what you do is you given the graph Laplacian for a network, you find the eigenvalues, right? So for these two networks over here, so here we just have one component, here we have two components, and this is what they look like. You write down the eigenvalues, right? So here you see you have a 0, 0.8 to 2, and so on. Here you have 0, 0, 2, 4, 4, and so on. It turns out that the total number of zeros, the 0 eigenvalues, tells you how many components there are in the network, right? And so this is true for this case, and this is true for this case, and I can tell you that is true regardless. Zeros in eigenvalues. So you have two zeros here, right? And it's true. Here you have two components, right? And for this network which I made earlier, it had 3 components, and sure enough, I had 3 eigenvalues. Pardon? Oh, I'm so sorry. I'm so sorry. Yes. Yeah. Okay, I'll fix that later. I'm so sorry. Yes, it's zero eigenvalues. Yeah. Yes. Sorry. It should be so. I mean, but you can see very clearly here, right? So basically, you have a 0. So that's just 1 0. So one component, 2 and 2, and so on, right?
If you try to diagonal into adjacency matrix itself, wouldn't that give you the idea ki how many blocks diagonal you have? Maybe? Like maximal connectedness kind of things.
So you mean starting from here, or like?
Yeah. I am asking if you block diagonalize the adjacency matrix itself, then the number of block diagonals that you have found would be equal to the number of.
Using what procedure? Yeah, you have to so you need some procedure to do that, right?
We don't know how to do block diagonalization of the matrix.
Well, I mean, so okay. In principle,
Block diagonals is related to multiplicity of
okay, but first, let's just this statement that I've made over here, right? That two eigenvalues means 2 components and so on. You may be wondering, okay, fine, why is this the case? I mean, so why is it working, right? So the reason why it works is the following, right? So this is, you all know this, right? Basically, to find the eigenvalues of a matrix, you basically if you for an associated eigenvector, if it has an eigenvalue lambda, you can express it in this form, right? Now it turns out that if you have this matrix over here, right, and this matrix, it turns out that it has a particular a very special type of eigenvector which is all ones, right? And you can see that basically when I do the multiplication, what do I get? I get +1 -1, and so then I get a 0, right? And then what about here? I get a +1 -1 +3 -1 1, I get a 0, and so on. And so I do this for everyone, I get 0 0 0 0 0. So obviously the eigenvalue has to be 0, right? So so this is something that it just comes out very naturally. And what about here? Well, here it turns out you can actually have this as an eigenvector. Basically, up to, I mean, for all the nodes that belong to component 1, suppose I have a 1, and all the nodes that don't, then so I have a 0, and so then if I do this, it turns out that that also is associated with a 0 eigenvalue. And I can also flip this as well. I can have all zeros over here and all ones over here. Use that. So basically, I can use an eigenvector like this or an eigenvector like this, and both of them have an eigenvalue of 0, right? Now, of course, here I've shown it. I mean, I've sort of grouped them together. Group component 1 and group component of 2 together, but they need not be grouped. I mean, this is just for you to see what's going on. But in general, like over here, it's completely at random. If suppose I had sort of sorted them according to component, you can see very clearly the 3 components that exist, right? But yeah, but basically, so that's a very simple sort of way to find the total number of components in the network by just simply looking at the Laplacian, finding the eigenvalues, and look at the total number of zero eigenvalues.
I mean, heuristically.
Yeah.
L is d minus a.
Yes.
So in the equation where you wrote L b equal to lambda times b.
Yeah.
So you will put d minus a and this eigenvector equal to lambda times that eigenvector. So when you break down, d multiplies with this eigenvector and the a multiplies with this eigenvector goes to the right side.
Okay.
So I think geometrically it seems like you want to see that in the direction of eigenvector. Do you have a neighbors degree? And then if this satisfies, then you can go with adjacency matrix, and then you, whatever factors is left, you can traverse by lambda times this.
Right.
Is it?
I mean, I get what you're saying. I mean, I think that's broadly correct. Yeah. But I haven't worked it out. But yeah, I think that is.
Thinking.
Yeah.
It's in the domain like geometric.
Sorry, it's geometric what?
Like, what is the domain to start with? Thinking in what direction? Geometric nature of this Laplacians graph.
Oh, you mean like what for this particular thing, right? So you're saying how to arrive at this structure? Yeah.
Can you do a space embedding like eigenvector direction?
I mean, likely. I mean, I'm not completely sure about that. Actually, I haven't looked into that, but it's possible. We can talk more about it.
Sir,
Yes.
what is this definition for weighted network?
Oh, yeah. You see that if you notice, actually, it's suppose I take this definition, and I just assume that it's undirected, right? Then you see that this is basically just ki, but this is just a generalization of this when it is directed. These two are exactly the same for the undirected network, but for the case of a directed network, I have to specify that this way.
Directed or weighted?
Oh.
There is no direction.
Oh, I'm sorry. I'm sorry. I completely yes. This is only for the case of an undirected network. I'm sorry. Yeah, for a case of a weighted network, what we do is that basically, yeah. So we essentially what we're doing is we are sort of assigning the node weight as well in terms of so the degree for a given degree, basically you're going to just add up all the weights. So, but essentially it'll follow the same maths. I mean, exactly the same thing will work.
Adjacency matrix also has
That will also be weighted. Yeah. So both are weighted. Yeah. I'm so sorry. Yeah. Okay. Yeah. Just a couple more things. So okay. So now for the case, this is another concept which is called betweenness centrality. So suppose you have a network like this. And so if you look at all the the possible shortest paths between every pair of nodes, so if you list them out, right? So basically here between 1 and 2 you just have 1, between 1 and 3 you have 2, and so on. So basically I'm listing them out, and then I'm looking at the nodes that lie along the shortest path. So here it's 2 and 5, 2 and 4, and so on. So the betweenness centrality is basically just the fraction of times that a node is going to appear in the shortest paths between all the other nodes. Okay, so for example over here you see that 1 does not actually appear in the shortest paths of any other node, right? Because it's clear, because 1 exists over here, and so you cannot cross 1 to get to any other path. On the other hand, you seem to be crossing 2 a fair bit, right? So I'm crossing 2 over here, over here, over here, and so on. And even 3, you see that I don't need to cross 3 to get to any other node. So I can just look at basically all the occurrences, right? So basically, so 1 is not appearing at all, right? 3 is not appearing at all. 2, so between 1 and 3, it's appearing both times, right? So it's appearing like here and here, and then oh, I'm sorry. I think I'm sorry. There should be an extra. There should be an extra plus one over here. Yeah. So basically, it's appearing both the times over here. It's appearing here and it's appearing here. So it'll be 3. Yeah, it'll be 3. 4 is appearing half the times over here, not appearing anywhere else. It's appearing half the times over here. So half and half, 1. 5 similarly, it's appearing half the times over here, half the times over here. It's 1. Yeah. So this should be a plus 1 over here. I'm sorry. So then from this, basically, you find the betweenness centrality, right? So basically you see that 2 has the highest betweenness centrality. So this you can, I mean, more sort of succinctly put, you can just write it down in this particular form. So if sigma st is the total number, so is the number of shortest paths which connect node S and node T, and sigma st of V is the number of paths containing a given node V, then you can write down the betweenness centrality by taking the sum over all of these, right? I'm essentially following the same procedure that I just showed over here. Okay, yeah. So hopefully that, yeah.
We add half and half because like.
So why? Because you see between 1 and 3, 2 appears all the time. So 2 always appears between 1 and 3. So that's why I put 2 by 2. So but 4 appears only half the time over here, and again it appears half the time over here. So because remember we're looking at the total. So let's say between sigma st. So sigma st, if S is 2 and T is 3, then this will be 2, right? But sigma st of V, so suppose V is 4, then it'll be basically 1, right? So basically that's half. And similarly over here as well, there'll be another half coming from there. So that's how it works. So this part hopefully is clear, right? Okay. I think then maybe we can break because we've covered a lot. So next time around, so I'll just mention this in a second, but next time around, I'll get to the more advanced topics like random networks, modularity, hierarchy, and so on. But for the time being, I think so now we're basically done with all of the basic concepts. So I thought maybe this will be like a nice exercise for you to work on. So essentially, just either draw or take a photo of this network. You will leave it up for some time. This network has 10 nodes, and you should be able to now do all of this because all of these things are have been discussed. So try and find the average degree, shortest path in between these nodes, diameter, number of walks, and so on, right? So hopefully, I think by tomorrow, I think you should have all of this. And yeah, okay. So with that, I think I'll stop for now.